Okay, so this video here, we're going to discuss another reaction which is related to the hydration of alkenes. This reaction is called an Oxymercuration-Demercuration. Okay, and what this reaction does is it still converts, it would convert alkene into an alcohol, and the more substituted alcohol product. Okay, so there are some similarities with an alkene hydration itself. The important point here, okay, where this is different and where this is sort of has some advantages over a hydration reaction, as there's no rearrangement. Okay, there's no rearrangement in this reaction. And now you can relate this to the mechanism itself, because why do we get rearrangements? That's because there is a carbocation intermediate. So if we don't have a rearrangement in this reaction, that means we probably don't have like a full carbocation. Okay, there isn't like a real carbocation in the reaction. And we will see the mechanism. Okay, so an example for this reaction is, say we have this alkene. This reaction is done in two steps. Okay, so the first step, you react your alkene with mercuric acetate. That's a reagent that we're using here, in water as a solvent. And second step, you reduce an intermediate that's formed by using sodium borohydride. We will not go into the details of this reduction step. Okay, it's a little bit too complicated. So we'll not go into the details of the reduction step, but this oxymercuration part is this first step, and the second step is the demercuration part. So when we do this reaction, we will get this alcohol here, plus minus. Okay, we will get that alcohol. So now notice how, again, in this alkene, we have a secondary carbon here. That's where the carbocation would have formed, okay, if it went through a carbocation mechanism. And then there is a tertiary carbon right next to it, and the carbocation would have rearranged. Okay, so essentially what I'm saying is, if we did a simple hydration on this alkene, which would be dilute sulfuric acid, we would get two products here, this, and then we're going to get that other product. And in this particular case, this rearranged product would have been our major product. Okay, so we can actually prevent that from happening, and we can get this alcohol as a major product, if that's what we want. Okay, so this oxymercuration-demercuration reaction actually gives us the ability to do that, okay, to avoid any rearrangements from happening. So we'll look at the mechanism again here to understand why does it happen like this, and how come we can avoid this rearrangement. So if there is no carbocation, what exactly do we have? Okay, so before we get into that, I want to talk a little bit about the reagent itself. Okay, so the reagent that we are using here for doing this reaction is mercuric acetate. OAC. Okay, now mercury metal, not something good for us. Actually, it's toxic. Okay, it's a toxic metal, but you know, this reaction was developed at a time when that was well, developing a more interesting reaction was probably a bigger achievement than, you know, the toxicity of the metal itself. And then the metal toxicities, you know, those evolved later. Now we know that mercury is not something good for us, so we would not want to use this reagent. And there are other variations of this, other reactions that can actually replacement for these reactions. Okay, but again, I think it's a very classical reaction where we have like a very different sort of an intermediate, so that's why we study this. So mercury is a metal, and anytime when you have metals, if you look at the periodic table, like most of this is a transition metal. Okay, so most of these metals, I'm just trying to think if I can come up with a periodic table quick to show you something. Okay, yes. So there we have at the end of your chapter, of your textbook actually, sorry. Okay, so elements in this part of the periodic table, these are called transition metals. Okay, and one way to think about it, you know, just a very simplistic way of think about these metals is that whenever you see a metal, I want you to think about electrons. Okay, since they are like heavier elements, okay, they usually have a lot of electrons on them. Okay, so mercury, you can imagine that it has like electrons on them, like treat them as lone pairs in a sense. Okay, when you compare it to like oxygen or nitrogen, so there are unused electrons on them. So mercuric acetate in this particular molecule, the reagent that we're using, this mercury is in a 2+ oxidation state. Okay, because this oxygen is 1 negative, this oxygen is 1 negative, and what that means is this mercury is in a 2+ oxidation state. Now, this reagent, when it's in solution, you know, there is an equilibrium. It exists in like some equilibrium, where what happens is one of these acetates can basically like take its electrons and leave. So we get a species. Where this mercury now has a positive charge. It still has those extra electrons, not just 2, it has more. Okay, I'm just drawing 2 electrons to represent a lone pair, and plus it's going to give you the acetate ion. Okay, so we get a species like that. So with mercuric acetate, this mercury is in a 2+ charge, so that's sort of because it has a charge, you know, it is sort of acidic. You could treat it as a Lewis acid because it has a positive charge on it. Okay, a Lewis acid. And once we get this dissociation to happen, now we have a mercury which has a positive charge on it. So it is going to be more Lewis acidic because now that oxygen is gone. Okay, and this species here, okay, that's the one that's important, or that's the one that we will be using for doing this reaction. Okay, I'm going to erase this because I think we need a little bit more space here. So that's the equilibrium that exists when you have mercuric acetate in a polar solvent like that. Okay, so essentially what happens is, in terms of mechanism, and this mechanism would have some resemblance to the halogenation reaction of alkenes that we've already discussed. So we have our alkene. This reacts with this mercuronium ion. Okay, the mercuronium acetate that we have here. Sorry. So we have that. So the mercury is positive. Once we have the equilibrium, so what happens is the double bond, the pi bond in the alkene, goes and attacks the mercury. In fact, I want to show it slightly differently. So the mercury has a positive charge to it. So the pi bond opens up. This is nucleophilic. So it goes and attacks the mercury, which is electrophilic. Okay, but notice how the mercury has these extra electrons on it, which we can treat as lone pairs, use them as lone pairs. So while this attack happens, the same time, the extra electrons on the mercury, they do an attack back on the alkene, on the carbon where the carbocation would have formed, similar to the halogenation reaction. And so what we get eventually is a mercuronium ion. Okay, so Hg, and we have OAC, and this mercury would still have a positive charge on it because now it's missing that lone pair of electrons on it, the extra electrons that it had on. Okay, so we get a mercuronium ion like this. So this is Hg. Okay, so the mercury in the middle here. Okay, now once we have this, this is very similar to a bromonium ion. That means these carbons, they still retain some carbocationic nature. They're still positive. Okay, and the more substituted carbon here is going to have a bigger carbocationic or a more bigger del positive. Okay, while the less substituted carbon is going to have a smaller del positive. So once we get this mercuronium ion, then in a subsequent step, our solvent, which is water here, this can come and attack at this more substituted carbon, and it's going to ring open the mercuronium ion. So that bond leaves. So very similar to the halogenation mechanism. Okay, and what that would give us, an oxonium ion intermediate. So the oxygen now has one lone pair to it, and the mercury is now connected to that less substituted carbon. Subsequently, in an acid-base reaction, water molecule can come and deprotonate. Sorry, okay, I'll fix this later. The water molecule can come and deprotonate that oxonium ion to give us the alcohol plus a hydronium ion. So what we see here is because we have this mercuronium ion intermediate, we don't have like a free carbocation. There isn't a carbocation which can rearrange now. So the mercuronium ion basically prevents the rearrangement. And so now the water or the nucleophile in your system can only attack that carbon which was more substituted in the alkene. And that gives you the alcohol product. Sorry, we're not at the alcohol product yet, my bad. We get this product. I'll have to erase this. Okay, we get this product where we have a hydroxyl there. Okay, the water is not part of this, so we have water there. That's part of the other step, and we get hydronium ions along with this, so we get H3O plus. And so now we have this mercuric species connected to that molecule. So to get rid of that, so all of this here is part of this first step. So to get rid of this molecule, we do a reduction using sodium borohydride. And what sodium borohydride does is it removes this mercuric species and adds a hydrogen over there. So we will not go into the mechanism of that step, but essentially what happens here is in this step, you cleave this bond and you add a hydrogen in place of that mercury so that you get to your alcohol product. So that's the mechanism of an oxymercuration-demercuration. The advantage being there are no rearrangements, okay? Let's look at another example so that I can point out something else here. So if we had a different alkene again, okay, so let's say we have this alkene, and if we did one mercuric acetate, water to sodium borohydride on this alkene, the alcohol would go to the more substituted carbon after both of these steps are done. That's the product that we're going to get. Okay. Now, some important things to remember here. We need these 1 and 2, because if you don't have the 1 and the 2, so 1 and 2 means that they're 2 different steps. So you do the first step and then you do the second step. If you don't have 1 and 2, that would mean that you're putting all of these things together, and then the reaction is not going to work. Okay, there'll be no reaction. Okay, so it is very important that we do it stepwise, 1 and 2, so that has to be shown. The second thing here is, for this particular example, since there is no chance for a rearranged product to happen, we don't really have to do this. Like a simple hydration reaction would be sufficient, you know. But a case where the rearrangement is possible, that's where the oxymercuration-demercuration reaction would be more useful. So for example, if we had this alkene that we used in the dehydration video, if we had that alkene, and if we did an oxymercuration-demercuration, we are going to get this alcohol as our major product now. Okay, that's the only alcohol that's going to form. And again, we'll get enantiomers because the alkene itself is a flat species. So where the mercuronium ion is formed, it could form from the front face or it could form from the back face. So we will get both enantiomers of the product. Okay. I want to show a variation of this, and this would happen, let's say, if we change the solvent. What would happen if I change the solvent out in this reaction? So if we did mercuric acetate, but instead of using water, we used methanol. Okay. We used methanol as a solvent, and then we do this sodium borohydride step. So we've changed out the solvent. So think about what would happen when we use water. What happens in this particular case? We know we've seen this like several times. From water, we remove a proton, we keep the hydroxyl in our product. So when we use methanol as our solvent, the product that we're going to make, or the one that we're going to get, is going to remove a proton from methanol, keep the rest. So we'll have OCH3. So we have a chiral center there over again. But now our product is not an alcohol, but it's an ether. We were making alcohols, now we're making ethers actually. So there is a variation to this reaction just by changing out the solvent. You know, and that's always useful because you change out one reagent and you make a very different product. You know, so as far as chemistry is concerned, this is very useful, synthetically very useful, because by changing one thing out, you get a completely different product. So you can make more molecules that way. Okay, so that's the oxymercuration-demercuration reaction. Another method for converting alkenes into alcohols, the more substituted alcohol. The advantage, there is no rearrangement in this reaction. Okay, bye.